I'm requesting that the university will give us the paid version of Zoom so that we don't need to log out every 40 minutes. But anyway, I mean, they're still in the process. Okay. Otherwise, we can also do Google Meet. But my problem with Google Meet, I cannot annotate. I want to make annotation on the screen itself. So anyway, so let me share my screen now. This one. Okay, so we discussed this one already last meeting about the translational and purely translational and purely rotational movement in 6-dimensional space. So there are 3 dimensions in position and 3 dimensions in orientation. So for example, there are purely translation movement and purely rotation. Of course, in real life, there's a combination of translation and rotation. So now the question is, how do we control motion? Okay, for example, this person that's falling because of gravity, in order for us to alter the fall of gravity, probably we'll attach the person to a robot, and then we can alter the movement of the person so that it can simulate a difference, for example, in the gravitational force. So we can make the person feel like he's falling or he's diving on the moon's surface instead of in the earth. Yeah. Or we can increase the gravity, like probably we say that he's in Jupiter, and then he can fall much faster because the pool of gravity is bigger. Okay, so we know that there is a translation, there is a translational and rotational movement of one frame of this frame F prime with respect to a frame F. Okay, that is the basic principle of robot motion. We express the movement in terms of translation and rotation, again, of one frame, in this case F prime, with respect to another frame F. Okay, that is the basic problem that we are dealing with here. Okay, so then the question now is that how do we express those reference frames? Okay, to express them, okay, we attach a reference frame at each of the joint of the robot. Okay, there's reference frame here, base 0, from joint 1, this is base frame, joint, joint 0, base frame, joint 1, joint 2, joint 3, and at the end effector frame, joint 4. Okay, we are not discussing the convention now. I just want you to understand that there is this method of attaching a frame, a reference frame, to each of the joint of the robot. And then all we need to know now is express or know the relationship between one frame with respect to another. This frame 1 with respect to 0, frame 2 with respect to frame 1, frame 3 with respect to frame 2, and frame 4 with respect to frame 3. And then all these relationships are defined by a matrix. And all we need to do in order to know the movement, the rotation and translation. Are you seeing my mouse moving or no? Are you seeing my mouse moving?
Yes.
Okay. Yeah. All we need to know is that when we express the end effector frame position and rotation with respect to the base frame 0, all we do is multiply the matrix. This matrix multiplied by that matrix, multiplied by this matrix, multiplied by that matrix, so that the resulting matrix will define the relationship of frame 4 with respect to frame 0. We are not doing the mathematical expression of that yet. I'm just giving you an overall view. Okay, so now, so these are the reference frames. We say that we attach reference frames to any kind of robot. There's no other way of doing that except attaching reference frames, no matter how complicated the robot is. Okay, so now let's do the basic information of how do we express translation. That means purely X, Y, and Z position of one frame with respect to another. So in this case, frame 2. Okay, expresses, okay, immediately. Okay, anyway. So this frame 2, which is the red frame, with respect to frame 1, which is the black frame. So in this case, in terms of position, we express the position only as a vector with 3 components, x, y, and z components. Okay. So in this case here, your p vector, there should be a p here. It's not stated. Okay, let me say that. Let me put that one. There should be a p here, where this p is, or let me annotate. Okay, there is this p, which is position of frame 2 with respect to frame 1. Okay, and that p, this is that p, and that p is expressed in terms of 3 components, p1, p2, and p3. Okay, what does it mean? Well, when we are talking about position of the frame, we are talking about this point. Okay, let me change the name. The origin. Okay, this point of the origin with respect to the x, y, and z of the base frame. Okay, so when you say frame 1, okay, let's say, for example, this is your x, and this is your y, and that is your z. Okay, so of course x goes positive and negative. Yeah, so x goes up to here. Okay, and then let me red, green. Okay, y goes up from here, there. Y goes there, as well as over on the other side. Okay, and then the blue, and then the z. Okay, like that, negative side and positive side. Okay, now what do we have here? When we say 2 with respect to 1, that means this point with respect to the x, okay, which is this x, that is x, the y, and the z components of the vector, excuse me, 1, p2, okay, the vector 1, p2, that means the vector of p with respect to frame 1, okay? So now, where is frame 1? This is x, so we say that, for example, this point, this is the p1, okay? Okay, which is, of course, equivalent to 1, p2, the x component of 1, p2, okay? This part here, this part, and that part, okay? I think that's easy. We know that from vector, resolving vector components. Okay, that is this point with respect to the x-axis of frame 1. Okay, what about the y-axis of frame 1? So y-axis of frame 1 is this. So the component of that point, of this point, P, with respect to the y-axis is this. Okay, so this is P2, which is equal to the y component of 1 p2 y. Okay, that's clear, I think. Yeah, I mean, it's easy. We've been used to that. Yeah, so probably your z component. Okay, probably your z component is this part here, maybe where you have a z component like that. Yeah, maybe this is your P3, which is equal to 1 P2 of your z component. Okay, there you go. So yeah, all these things we know. Okay, it is just a position of that point. Okay, it is a vector 1 P2 whose end is this point. And we want to know how this position, the tip of that vector, is with respect to each of the components of the frame where we express this vector based upon on this frame one. Okay, when you say we express it based on frame one, we want to see the components of this vector with respect to the x of that frame, with respect to y of that frame, and with respect to the z of that frame. Okay, where we are resolving the components of the p vector with respect to the x, y, and z axis of frame one. Okay, I think that is understood. So now let's clear that one. Okay, now we understand this part. Finish. Okay, now the tricky part actually is the rotation. Yeah, there are many ways of expressing the rotation of one frame with respect to the other. So the most prominent one are in terms of rotation matrix, which we are discussing about. We're discussing in this class. Or the other part, or the other method, is about Quaternion, which is expression of again rotation based on 4 components. Yeah, Quaternion, as the name implies, there are 4 components. In our case here in the rotation matrix, there are 9 components. Okay, so that means that there are some redundant information in the rotational matrix. But anyway, we are doing rotation matrix because it's easier mathematically. It's a lot easier to combine the rotation and the position in terms of a matrix form. Okay, so now let's see how do we express each of these components then with respect to each of the components of frame 2, in this case our frame 2, which is the red component, with respect to frame 1, which is the black frame. Yeah, so now how do we do this? Again, it is about a vector. Yeah, but in this case our vector, when we're discussing about rotation matrix, we need to note that the vectors are units, unitary vector. So in this case here, you say unitary vector. Unitary vector when we are discussing about rotation. Okay, so that means that this vector component of for example, we say that this is the x component of frame 2 and the y component of frame 2 and the z component of frame 2. We say that this vector, this exact vector that we are considering, is a unit vector. Okay, that is that the norm is equal to 1. Okay, the norm of that is equal to 1, everything. Okay, and the norm of this is equal to 1. That means that, how do we say that? Well, with respect to the frame itself, we say that x, okay, with respect to frame 2 is actually equal to 1, 0, 0. Okay, and then the y, frame 2, with respect to frame 2, is actually 0, 1, 0. And the z with respect to, from frame 2 with respect to itself, is equal to 0, 0, and 1. Okay, so if we express all those components with respect to itself, how does it look like? Well, if we see, for example, if we look at up here. Okay, well, if this was frame 2, if that was frame 2, well, if this is your x, y, and z, okay, well, this one extends over there. Yeah, extends. Yeah, this one is length 1. Okay, this one will also extend. Okay, this one is length 1 also, and this one extends up. and also extends down. So that one is 1. Okay. So, well, if this is 1, what is this vector? If this is 1, okay, x is 1, y is 0, and z is 0, correct? So this is 1, 1, 0, 0. So here, the same thing, y is 1, but x is 0, and z is 0. So this one is 0, 1, 0. Yeah. And z, same thing, z, this is 1 in terms of z component. So the rest of them are 0, so it's 0, 0, 1. Okay. And how you take the norm? Well, just to review, okay, just to review the norm. What is the norm of the vector? Okay, it is what? The norm of a vector, for example, of x is equal to, okay, if it's three-dimensional, then it is the square root of, okay, x, the first component, maybe the x component, plus x, okay, this is squared, x of the y component, plus the x of the z component. Okay. So that means that what? For example, if your x is equal to, so what is the norm of 1, 0, 0? Okay. What's the norm? What is the norm, by the way? Norm is the size, the dimension, okay, the strength of the vector. Okay. So now, what is it? In this case, this is square root of 1. That's 1 because that's 1 plus 1 squared, okay, plus 0 plus 0. Okay. But now this is all 0. So 1 squared, what is 1 squared? Is 1 squared of 1. That is just equal to 1. Okay. That's why they are unitary vectors. Yeah. The norm is 1. Okay. So all of them have norm 1. This one norm 1. This one is also norm 1. That one is also norm 1. Okay. So that's important thing that we need. Okay, it's running out of time, but I'll just log in again. Okay, anyway, let's continue until it stops. So now we are clear about that. So each of these vector components of your x, of your y, I mean each of these axes of your x, y, and z axis of frame 2, when we are considering rotation, we want to consider them as unitary vectors. Okay, so now those unitary vectors, how do we express them in terms of frame 1? Okay, so we say that this is the x vector, okay, of frame 2. This is the y vector of frame 2, okay, and this is the z vector of frame 2. This entire thing. Okay, this entire thing is the x vector of frame 2. This entire thing is the y vector of frame 2. This entire thing is the z vector of frame 2. Now expressed with respect to frame 1. Okay, so now expressed with respect to frame 1. Okay, so now we want to know this x. Where is your x of the frame 1? So let's just assign this one. This is the x of frame 1. Okay, this is the y of frame 1 and the z of frame 1. Now we are saying that we want to express your x, which is the x, this x. We want to express your x, okay, in terms of the x, y, and z component of frame 1. The same thing as how we expressed this vector before in terms of frame 1, although this vector is not a unitary vector. You understand? Okay. What we need to do now is express all these vectors, this vector x, this vector y, and this vector z in terms of frame 1. Okay, so this is vector z, I mean vector x of frame 2. This is vector x of frame 2 in terms of frame 1. So we want to know what is the component of that with respect to x. And then what is the component of that with respect to y, which is of course, this is the component with respect to y, this one. And this is the component with respect to z, this one. And the component, I mean, with respect to x, sorry, with respect to x, with respect to y, and the component with respect to z. Okay, so maybe this is like this. Okay, it's a wrong drawing. Okay, hold on, let me correct it. Let me clear everything. Okay, let me draw it properly. So now this is your x of frame 2, and this is your x of frame 1, y of frame 1, and z of frame 1. Okay, so now this is your x of frame 2, y of frame 2, and z of frame 2. Now we want to express, let's start first with the x2, yeah, this x2. y2 and z2. And then let's say x1, y1, and z1. Okay, so let's express frame this one, x component. We say that this one, okay, is that goes up a bit. Okay, this is the x component, and this one is the y component. Okay, so this is the z component. This is the x2, okay, x component. This part, yeah. Is that one? Oh, no, I don't need to do that. Okay, and then this one is the x2 y component, and this up here is the x2 z component. Okay, so that means here this is your x2. When you express x2 with respect to 1, okay, so this is your x2 of the x component, x2 of the y component, and then x3, I mean, yeah, x2 of the z component. Okay, so once you express this x vector with respect to each of the x component, y component, and z component, then you express x2 already with respect to 1. We express x2, the vector x2, with respect to frame 1. Okay, this part is your vector x2 with respect to frame 1. Okay, now we express x2 with respect, I mean, not x2, but y2 with respect to frame 1. So again, y2 with respect to frame 1. We will just repeat the process, but now it will be y2. Okay, this is the y. Yeah, so express the y in terms of maybe, for example, this one goes down, this one goes down, so it goes down like that. Okay, so here, this is your y2 z component, and then, okay, sorry, it should be the other way around. Okay, y2 z component, and then this is your y2 of the x, because this is the x here, x component, and then this is y2 of the y component. Okay, y2 respect to y. Okay, so now once you get those components, you express already y2 with respect to frame 1, and so you have y2 with respect to the x of frame 1, y2 with respect to the y of frame 1, and then y2 with respect to the z of frame 1. So the same thing we have to repeat